Hello and welcome back to Calculus 1. We are starting chapter 5, which will focus on integration. So first section is on approximating areas, and there will be no integrals here. This is actually something that will become application of integration, the main application, main focus of integration. So we are first going to take a look at how to approximate area under a curve, and then we are going to move back to exact areas. So we start with exact shapes that you already know, then we move to approximation, and then in 5.2 we move back to exact, and then we start talking integration. The most important sections, well, two sections, the most important are 5.5, use substitution. If I haven't mentioned before, you know Calculus 2 is coming, right? In Calculus 2, you have two chapters on integration, chapter 6 and chapter 7. Much of those two chapters is how to manipulate integral and algebra and everything else to turn it into 5.5. So if you don't know 5.5 and you're not planning to learn 5.5 in between two classes, do yourself a favor and don't sign up for Calc 2. That's as simple as that. So Calc 2 is going to be, first two chapters are going to be integration, mainly focusing on 4, 9, 5, 2, and 5, 5, but 5, 5 primarily. And then the second two chapters, 8 and 9, it's going to be limits, 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 and some proofs. And then chapter 10 is combination of all, that is trig, 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 trig. So we'll talk about requirements for Calculus 2 and your prep for Calculus 2 next Saturday. I will give you some of the hints of what you should do in between this class and whenever your Calc 2 is. So let's take a look at approximating functions. First, we have shapes which you guys are familiar with and you know. This is square, and you know that area is a squared. You have a rectangle whose area is a b. You have a circle whose area is pi r squared. Does anyone know ellipse? Area of the ellipse? Pi AB. Now, can we just connect all of these formulas that we see? Connect circle with a square and a rectangle with ellipse, and see that you introduce pi and just round it. Bueno? Good. We have a triangle shape with a height and a base b, which is 1/2 base times height. We have trapezoids, a, b, and the height, with the area a plus b over 2 times the height, and so on. So these are the exact formulas. There is more, obviously, for any shape that is regular, we know it. But now we are interested in what can I do if I have a function rather than a shape that it's like this. Can I find the area under square root of x? Right? That's the question. So let me partition it and try to find area on 0 to 4. So what I did is I partitioned it at every whole number, so 1, 2, 3, and 4. And now what I can do is I can draw rectangles, and rectangles can approximate area. Now I have choice for each one of these regions to pick left corner or a right corner to draw the rectangle. Let's just draw the first thing to understand what I'm saying. So in a first, between 0 and 1, if I pick to draw the rectangle from 0, well, I'm just going to draw a line like that, and there is actually no rectangle. It's just going to be 0, right? So I can do that. Or I can do this and draw the rectangle to the left. So I can pick the left point and draw a rectangle to the right, or I can pick right point and draw the rectangle to the left. In one case, rectangle is 0. The one case, rectangle is going to be whatever the value, which is 1 actually. So now, which one do we pick? Well, both actually. We are going to define left and right. So left-hand sums and right-hand sums for this. So what I want to do first is I want to use the left corners first. So I'm going to create all of my rectangles by picking the left side and draw these horizontal lines. So that's what I'm going to do. So you see that the first rectangle has 0 area, the other 3 do not have 0 area. Now I need to know what is the height for each one, right? Because the area of the rectangle is length times width, or base times height, whatever you want to call it. Height is clearly y value of the function. Because when you compute your function, right, at 1, you had square root of 1 is 1. At 2, square root of 2 is square root of 2. At 3 is square root of 3. And at 4 is 2. Right, square root of 4 is 2. So heights are given by simply computing the function at the point where you are considering your rectangle. So now, if I want to approximate area with the areas from the left, it's a left point that gives you the rectangle, right? So in each one of these, you have 4 rectangles. For all 4 of them, you see that the rectangle emerges out of the left corner. So what do I have? I have the base is 1 times the height is 0, plus the base is 1 times the height is square root of 2, plus the base is 1 times square root of 3. Oh, I skipped 1. Hold on. 1, 1, root 2, root 3. There we go. So the first rectangle over here is this. The second rectangle over here is that. The third rectangle over here is this one. And the last rectangle over here is that one. So we have 4 rectangles, and we have 4 rectangles in our calculation. All I need to do now is to use the calculator to come up with decimals, and that will be approximating the area under the curve. Why is it approximation? Because it's not exact. So I'm going to remove all these arrows and these things. So what do I have to do over here? I just have 0 plus 1 plus root 2 plus root 3. And we have 4.15. 4.15. So if I use the left-hand sums, now there's a lot of error here. See, all of this stuff over here, plus all of this stuff, plus all of this, and all of this, that is all error. The difference between the exact actual area and the one we calculated. So let's do the same thing, but from the right. So I still have the same square root function, 0, 1, 2, 3, and 4. But this time around, I'm going to use right points on each. So I am creating these rectangles which are actually taller than a function this time. And these rectangles now will give me area bigger than what I need. And again, all of this stuff over here is error, but now the error goes to the other side. So this now blue is error again. We are approximating. All right, so what is the approximate area now? Area approximated by area with the rectangles from the right is, again, we still have our 1, 1, 2 root 2, 3 root 3, and 4, 2, because we need those heights. So the first width, well, each of the widths is 1, but first width is 1, and the first height is 1. Plus second width is 1, and the height is root 2, plus 1 times root 3, plus 1 times 2 as the y value. 1, 2, 3, 4 calculations for rectangles. Good. So now we have 1 times 1 is 1, and then 1 times 2 is 2, so that's 3 plus root 2 plus root 3. And I have 6.15 on this one. So what I know is that the exact area is in between 415 and 615. Now go ahead, average if you want to. You know, if you average these two numbers, you will get 515, and you can say, okay, area is about 515, because, you know, you can average and see. The most important part for us to understand here is that we can use the left-hand sums, we can use the right-hand sums. Why sums? Because we will be adding all of those areas, so we call them sums. It's the area of each individual rectangle added to the next one, added to the next one, right? So we add individual rectangle areas to come up with this. So this is a lot of error. Everything that it's painted red or blue is error, and it's significant amount. Can I make this better? And the answer is yes. I'm going to take the same problem, but this time around I'm going to pack twice as many rectangles. As soon as I do that, the amount of error is going to reduce. So what I'm going to do now is I am going to increase the resolution, right? We're dealing with the same function. We're dealing with the same interval, 0 to 4. Yes?
of the same as the square root is what's supposed to be the square root of x?
It's the square root of 2, square root of 3, and then square root of 4, which is 2. Oh, yeah, this is supposed to be square root of x. Yes. Okay. Thank you. Yes, that's a function. Good. Draw the same shape and partition over whole numbers first. 1, 2, 3, 4. And then partition in between. Now these partitions are 1/2, 3/2, 5/2, and 7/2. This is still a root x. And now we have double the amount of rectangles. If I use the left we will be creating 8 rectangles. And what you see just in the first one, if you focus on the first one over here only, it used to have this here, used to have that one as a part of the error. See that? That was the part of the error, right there. This part over here used to be part of the error, but now that part is no longer error. This part now is going to be calculated in the area, which is the one that I labeled right there. So we are significantly reducing error. Yes?
That's 7/2, right?
7/2, yes. It's clearly 7 if you look at it, see? With a V. So now we have a lot more writing to do. Please note that each one of the intervals now is a 1/2 width, and I'm just going to label each one of these intervals with delta x, because delta x is defined as x2 minus x1, right? The difference between the two. So I'm going to write the formula for delta x. It's b minus a divided by n. And in our case, delta x is 4 minus 0 divided by 8 rectangles. It's 1/2. So each one of these divisions over here has delta x in it. Each one of them. And each delta x is equal to 1/2. Now I'm also going to label these points as x0, x1, x2, x3, x4, right? And go all the way to x8. So now what is the typical area? Well, I'll explain AI in a second. It is going to be delta x times f of xi. So this is area of individual individual rectangles. Now this I is a counter. Those of you into programming and computer science and so on, you know very well what I is. It counts 0, 1, 2, 3, 4, 5. So I get to approximate the area by using the left-hand sums. And now I have delta x, I'll write the formula later, 1/2, which is delta x, times the function computed at 0, which is 0, plus 1/2 times the function computed at 1/2, which is square root of 1/2, plus 1/2 times 1, plus 1/2 times square root of 3/2, plus. So all I'm doing now is I'm writing areas one by one, and I'm computing heights at each one of the values and multiplying by delta x. So for the first point, the height is 0 and the width of the rectangle is 1/2. So there it is, 1/2. And for the second rectangle over here, the height is computed at 1/2. So that's the height, and then delta x is the width. So width times height. So the first one is always 1/2, which is delta x, and the second one is function computed at the value for that. So the next one is root 2 plus 1/2 square root of 5/2 plus 1/2 square root of 3 plus 1/2 square root of 7 divided by 2 plus 1/2 times 2. Wow. We don't want confusion. We can use English or Arabic. Which one would you prefer? Arabic? Okay, I'll switch to Arabic then. 7. You know these are Arabic numbers, right? Yeah. You picked up Latin alphabet, which is A, B, C, D, but you didn't pick up Latin numerals. Right? Roman numerals, remember those? That's 1, 2, 3, 4. So there's a mismatch a little bit, but that's okay. So we'll use our Arabic numbers. And now you compute all of this, right? So that's the first one is 0, so we don't have to worry about that. The last one is 1. So I'm going to compute. Now, do you guys see that you can factor out 1/2, that each one has 1/2, right? So that's the key. We are actually going to factor out the delta x for our calculations later. So I'm going to factor out 1/2, forget about 0. So I have square root of 1/2 plus 1 plus square root of 3/2 plus root 2 plus root of 5/2 plus root 3 plus root of 7/2 plus 2. Oh, you wanted out of it. There we go. Now, compute. and the number I get is 5.77. So you see that the value is much closer to the average. Remember that we averaged everything to 5.15, right? So it went from 6.15 to 5.77. That's closer to 5.15. So it seems that it's getting better. And it does get better. It is getting better because you can see that clearly in the picture. So what happens simultaneously as you pick more rectangles? What happens? It gets more accurate, and at the same time, this is the one you're thinking about. Did you say annoying? Yeah. Now I'm seeing things. So what happens as we are getting more accurate, right, with more rectangles? What else is happening? Yes, it's more annoying to compute. Exactly. How do we get the better answer over here? Double it again. Go every quarter. Now that is going to have, instead of 8 calculations, going to have 16 calculations. Right? So it gets worse, progressively worse. How do we get exact? We get exact when we send the number of rectangles to infinity. I know. So you sit and calculate that one, right? But then you said you can't prove immortality, so now you're looking at the problem and you say, well, how are we going to ever achieve to get, exact area calculated? We'll get there. For now, it's important just to understand that you can take a curve, which is not one of the regular shapes, put some number of rectangles. It doesn't matter how many. You can put 6 rectangles, you can put 9 rectangles, you can put 10, whatever. And understand that as you add more rectangles, as you cram more rectangles in the region, interval, prescribed, like in our case 0 to 4, the more rectangles you put, the better precision in terms of your answer. But in the end, this is all approximation. Now, you will see later that these approximations actually get very quickly very good. So if you're asking the software to do these calculations, software does it quickly, over 10,000, rectangles. And it gives something that we can interpret as the exact area. Because the amount of decimals that will be exact is huge, right? And we generally don't deal with numbers that are that small. Very few, very picky industries, right? So we can approximate area. So now I would like to just write this in a concise form so that we don't have to write this over and over and over again. The first thing we're going to do is say that the area is approximated by, and you know that we are supposed to pull delta x out, and what's left is f of x0 plus f of x1 plus f of x2 plus f of x3 plus ... going on to f of xn, right, whatever the amount of rectangles. And at the same time, delta x is b minus a over n. This is our formula. If you want only 3 rectangles, you will keep 1, 2, 3. If you want 4 rectangles, next one is added. 5, 6, 7, whatever amount of rectangles you have, you will just expand that using the function over here. And delta x is given as b minus a over m. But now, writing all of those things, x0, x1, x2, x3, is there a better way for that? And the answer is yes. Now we're going to learn summation notation, because summation notation helps us actually write these type of progression in like x0, x1, x2. We can actually write the entire parenthesis as just one thing. So I'm first going to write it, and then I'm going to explain. So delta x times the sum of all f of x i's, where i's go from 0 to n. Now, those of you into programming, you say, of course, clearly, common sense, right? So I want to talk to those of you who are not into computer science and programming now. This I is a counter. The sigma over here represents the sum. So it starts with this number and ends with the number on top. If you now look at this and then look at the exploded version up there, the first time around is delta x times f of x, pick up 0. Summation means plus, so plus. The second time around, delta x times f of x1, because the next whole number after 0 is 1. So this I is going to go through 0, 1, 2, 3, 4, 5, in order, maybe all the way up to 8. So S0 through, I is equal to 0 to 8, gives us x0, x1, x2, x3, x4, x5, x6, x7, and x8. So that's what we have for this. This is called summation notation. And we actually, as the last part of 5.1, we are going to discuss and talk about summation notation. So I'm going to actually remove these guys now, and I'll add them again once I talk about it. So summation notation. Sigma means sum, add, addition. And a simple example to understand would be summation I goes from 1 to 6 of I. Well, as you go through cases, right, you start with 1, so I is 1, and then summation plus, the next time around is 2, plus, the next time around is 3, plus 4, plus 5, plus 6, stop. It says when I is equal to 6, you stop. So we got to I equals 6, and then stop. Now you can actually add these numbers, get 21, and be done, right? This is another summation. I starts at 2, ends at 5 for I squared. Okay, the first number I gets to take on is 2, because this is where it starts. So I is 2 and then squared. You have to follow the formula. Summation, so plus. Next time around I is 3, so 3 squared. Plus 4 squared plus 5 squared. So all I've done is I worry where I start, which is I equals is where you start with a counter, and you plug that I in the formula, and whatever it gives you on the other side, you write it. So this is 4 plus 9 plus 16.
54.
Yes. 54. Summation I starts at 0, goes to 4 of 3i plus 2. What do you get? Alright, so now, if you have this, you're correct. 3 times 0 plus 2, plus 3 times 1 plus 2, plus 3 times 2 plus 2, plus 3 times 3 plus 2, plus 3 times 4 plus 2. And I have to stop because I reached I equals 4, which is the top of the sum. Once I have that, I can compute. I have 2 plus 5 plus 8 plus 11 plus 14. Alright, so that's 10, 20, 10, 20, 30, 40. So I hope you have 40 at the end. So I hope that you see this location, which used to be I in the formula, go from 0 to 4. and the shape of the entire function, like 3x plus 2 is 3i plus 2, the shape stays the same parenthesis to parenthesis. We're just updating I as we are moving from one to another. Do we all see that? All cool? Good. Now just one cool property, and we can go and start 5.2. So if you have constant in the sum, you can kick that constant outside. See, the function is in terms of I, just like it was here. Function is in terms of I. I is its variable, not x, I. So, in the i's of the sum, the variable is I, because that's what's changing from 0 to 1 to 2 to 3. So, you can't take f of I and kick it outside because it operates on i's. But c, right, it's a constant. You can also kick out x, because x is not variable for sum. I is a variable for sum. X is not. So, when I have delta x f of x0 plus delta x f of x1 plus delta x f of x2 plus going on forever, I can say, oh, great, I just have 0, 1, 2, 3 and as an index, so I can say sum all delta x f of xi from I goes from 0 to, let's end it at some value n. And now the rule from the red rule from above kicks in. Delta x is actually a constant. Yes, there is x there, but the variable for summation is I. So I can kick delta x outside and just have summation of f of xi from 0 to n. Generally, we don't write I equals because we know it's I equals. So we just write 0 to n, or 1 to 3, or 1 to 5, whatever. So that's just a little bit of this summation notation, so you guys are not freaking out when you see some of the stuff in the future. And basically, chapters 8 and 9 in Calc 2, they're covering sequences for one lecture, and then series and power series, which is chapter 8 series and chapter 9 power series. So that's that. I'm going to restart the stream for 5.2.